Into section 3.5, and we're focusing on functions that have complex zeros to them. Everything in the last couple sections we were focusing only on real zeros, okay? And there's a lot going on in this section, lots of different examples that we need to get through, okay? Let's first begin with the fundamental theorem of algebra, okay? It says that every polynomial function f of x of degree n greater than or equal to 1 has at least one complex zero. So in the past, we were always talking about the degree of the function will tell you at most how many real zeros of the function that you have. That was in terms of real zeros. Here we're focusing on complex zeros, which could include the real zeros, but doesn't have to. Okay, so basically we're stating that if the function doesn't have any real zeros, it still has to have at least one complex zero. Okay. This also can kind of segue us into what's referred to as the linear factorization theorem, or it's sometimes called the complex factorization theorem. It says every polynomial f of x of degree n greater than or equal to 1 can be factored into n linear factors of the following form. A sub n, f of x equals a sub n times x minus r sub 1, x minus r sub 2, up to x minus r sub n. A sub n, r sub 1, r sub 2, r sub n, these are all complex numbers, okay? Now understand, these are all considered linear factors because the powers of x on each of these are 1, okay? So we're saying that every function could be factored in terms of all linear factors, basically, in this theorem, okay? Now, let's move into another theorem, and this is one that you probably saw in Algebra 2. This is your conjugate pairs theorem, and it says that for any polynomial function f of x, irrational and complex zeros, they have to come in conjugate pairs. So that means, let's say 3 plus 2i is a 0. Well, the fact that that's complex, that means by this theorem that its conjugate, 3 minus 2i, also has to be a 0 of the function, okay? Similarly, 1 plus the square root of 2, that's an irrational 0 in its exact form. If that's a 0, then 1 minus the square root of 2, its conjugate has to be equivalent to, or has to be a 0 of the function, all right? And this theorem right here, this kind of relates back to Descartes' rule of signs. If you recall, in that theorem, there was a part where you had to take your number of sign changes and you had to subtract it by an even integer. And that could also give you your possible number of positive or negative zeros. Well, the reason we were subtracting by an even integer was because of this conjugate pairs theorem, right? Pairs mean pairs have to come in even numbers, right? 2, 4, 6, and so forth. So if you weren't a positive 0 or you weren't a negative 0, then you had to be a complex 0 where you would be coming in pairs. That's the reason for that in Descartes' rule of signs, okay? So let's get into some different examples where these theorems that we've just discussed are coming into play, okay? Let's form a polynomial function of least degree, meaning the smallest degree possible, with integer coefficients, meaning no fractions, no decimals for our coefficients, that has zeros of 2 plus 3i and 1/2 where the multiplicity is 2, okay? So right away I can use my conjugates theorem here, and I can say that if 2 plus 3i is a 0, so is 2 minus 3i. It's also got to be a 0, okay? So in total, by the fundamental theorem of algebra, I'm working with 4 total zeros here. This is 1, this is a second 1, and then 1/2 can be considered twice with its multiplicity of 2. So that means I have a total of 4 zeros, making the least degree 4. Okay? Now I bring the linear factorization theorem into play. I'm going to take each one of these zeros and make a linear factor for it to build the function f of x. So if 1/2 is a 0, then 2x minus 1 would have to be a linear factor of the function. And notice I have it twice because of the fact that the multiplicity has to be 2. Okay? I can build 2 more linear factors using my complex zeros of 2 plus 3i and 2 minus 3i. Notice all I need to do is take 2 plus 3i and subtract it from x to build a linear factor for the function. And I do the same thing for 2 minus 3i. I subtract it from x to build the factor. Okay? So this is your complete linear factorization for the function in terms of all the complex zeros. Okay? Now what we want to do is we want to multiply this out and put it in its expanded form, which can be a little tricky. Okay? So there's some tips that you really want to focus in on at this point. Okay? So first, notice I'm multiplying these two together to give me 4x squared minus 4x plus 1. Okay? And then I'm going to try to multiply these two factors together, but I'm going to use a little trick first before I actually do that, okay? If you just try to multiply this straight out right now, it can get a little messy, all right? So notice what I'm doing here. It's a regrouping process. I'm distributing the negatives that are in front of each complex number, okay? And when I distribute the negative here, it makes that minus 2, and this becomes negative 3i. When I distribute it here, it becomes minus 2 and positive 3i. Once I distribute that negative, I'm actually able to shift my parentheses to being around x minus 2 here, as well as x minus 2 here. And this is beneficial because if you notice, this set of brackets is the conjugate of this set of brackets. Literally the only difference between the two is the minus in front of 3i here and the plus in front of 3i here. So if these are conjugates of each other, when I multiply them out, I really only have to do the first and last parts of FOIL. I don't have to worry about x minus 2 times 3i and negative 3i times x minus 2 because those will just end up canceling each other out. Okay? So when I do the first part of FOIL, x minus 2 times x minus 2 gives me x squared minus 4x plus 4. And then negative 3i times 3i gives me negative 9i squared. And then understand these are like terms. These are both constants because negative 9i squared is really positive 9. Recall I squared is equal to negative 1, right? So 4 and negative 9i squared become 13. Okay? Once I'm here, this should be smooth sailing. I can use the distributive property. I'll multiply this trinomial by this trinomial just using distribution. It'll give me several terms, which I can then combine the like terms to get to my final function right here. Okay. Now, I do want you to notice what's in red. Your answers can vary depending upon the choice of your leading coefficient. So right now, the leading coefficient is 4, but there's nothing that says that I couldn't take like all of these and multiply them by another constant. So that's kind of what I have down here. Had I taken and multiplied all this by 2, I would still have a function with the same zeros. The only thing that would change would be the y-intercept of the function. Okay, so really what we're getting at is this number out here, it's unimportant for the zeros of the function. Only it affects is the y-intercept of the function. Okay? All right, second example. Use the given 0 to find the remaining zeros of the function. Okay, so here's the overall function, and we're told that x equals negative 5 is a 0 of the function. Okay, well, notice the degree of this function is 3, so by that fundamental theorem of algebra, there's going to be 3 complex zeros to this function, okay? So right here's one of them. Conjugate's theorem says that 5i should also be a 0. So there's a second one right there. So I already have 2 of the 3, okay? Now, what I'm going to do is use these 2 to make linear factors. So I subtract each one of these from x to make their linear factors. And notice when I subtract negative 5i from x, it really becomes x plus 5i. I multiply these linear factors together, and it takes me to x squared plus 25. Okay, so this is now a quadratic factor of f, and to find the remaining final factor and then the final 0, all I need to do is long divide it from the original function to get my remaining factor and my remaining 0, okay? Notice when I long divide this into the function, I get a remainder of 0. That remainder being 0 is proof that this is in fact a factor of the function, okay? If this were not a 0, then I either messed up in the division process or I didn't build this correctly using the 2 zeros I already knew, okay? Notice this result of x plus 3. What that's saying is that f of x has a factored form of x plus 3 times x squared plus 25. And that means that if x plus 3 is a factor, then x minus 3 is the remaining 0. So you've got this 0 along with the 2 other imaginaries for a total of 3 complex zeros. Okay? Understand this is it's a real 0, but it's also complex, right? Along with these 2 are imaginary, but they're also complex. Okay? All right, third example. Find the complex zeros of f of x. Okay, so all we're given is the function itself in its expanded form. We want to find its complex zeros, which is basically stating find all the zeros, both real zeros and non-real zeros. Okay, and then we want to write the function in its complete factored form. All right, so first thing I've done here is I've used Descartes' rule of signs to help me kind of start to narrow things down. There's only going to be one positive 0 because there's only one sign change in the coefficients of f of x. And then that means one positive real 0. And then here's f of negative x. There are 3 sign changes. So there could be 3 negative zeros or 1 negative 0 by Descartes' rule of signs. Okay. Notice the degree of this function is 4. So if I have 1 positive real 0 and 3 negative real zeros, that's 4 total real zeros. So that's one possibility. Or you could have 1 positive and 1 negative for a total of 2 real zeros, and that would just mean the other 2 would have to be, complex. Okay. So now I use the rational 0 theorem to help me come up with some of the real zeros for this function, okay? So I make my list of p over q's, and then I start testing them with the synthetic division here, okay? And notice the first value that gives me a remainder of 0 is negative 2, okay? So that means the function can now be slightly factored. If negative 2 is 0, then x plus 2 would have to be a factor of the function. And then these 3 numbers these 4 numbers right here lead me to a cubic factor of the function, this whole piece right here, okay? Now once I get down there, I now have to use this cubic to find the other zeros, okay? And what's nice about this one is I'm noticing that it factors by grouping, okay? It factors by grouping. I can pull an x squared out of these 2. I can pull a 9 out of these 2, which will make x squared plus 9 as a factor. And then I'd be left over with 3x minus 1 in each of those, okay? So this would be your complete factorization for the function. That's because x squared plus 9 doesn't factor anymore, okay? And then I can reason out my other zeros pretty quickly here. X squared plus 9 is going to lead me to plus or minus 3i, and 3x minus 1 is going to lead me to 1/3, along with the negative 2 that I already had. Notice there's 4 total zeros. You have 1 negative real zero, 1 positive real zero, which matches Descartes' rule of signs, and then we have the other 2 zeros. They are imaginary. Okay. All right. So I know I threw a lot at you in those 3 examples. If you need to, go back and kind of watch the explanations of each one of those again as you try to complete practice 1 on your own. Okay. So pause the video. Try to work through practice 1 yourself. If you get stuck, come back and look at these examples again. Okay. Then you can start the video back up and check your work with mine.